Hello everyone, welcome to In 5 Minutes. In this video clip, we will discuss one question on maximum power transfer theorem. The question says, find the value of resistance R, which is connected in the network here, for maximum power transfer to it, and also find the value of P max, which is the maximum power. Such type of questions which are based on maximum power transfer theorem, we have to remember two things. Number one, the maximum power is transferred to a resistance R from the network if the value of the resistance is equal to Thevenin's resistance of the network, that is RTH. Point number two, the maximum power can be calculated using the simple formula, which is VTH square upon 4 RTH. In simple words, maximum power transfer theorem starts with Thevenin's theorem. So we have to first find VTH and RTH, and then at the end, once I know VTH, RTH, I can answer both the questions on maximum power transfer theorem. So let's start, and let's in fact start with finding of VTH. That will be my step number one. So in step 1, we are going to find VTH. So to find VTH, we have already seen this in some previous questions, that to find VTH, which is also called open circuit voltage, you have to remove this resistance R and obtain open circuit terminals across which define the voltage VTH. So let's do that first. So I've removed the resistance R, and I'm going to now define voltage VTH across this open circuit terminal. So I'll take upper terminal, let me call it point A, and lower terminal point B. I'm assuming point A to be at positive polarity and point B to be at negative polarity. So this particular voltage, I'm going to mark it as VTH. So let's find out VTH in this particular circuit. We can use any method of analysis. We can use mesh analysis or nodal analysis to find out VTH. Now, if you observe in this particular network which is given to us, if I plan to apply nodal analysis, then I will have to first figure out how many nodes are present in the circuit. So you can see this is one node. This whole thing will act like one node. This is my node number 2, and this bottom line will be node number 3, which can be taken as the reference node. So once I take these 3 nodes, out of which one is the reference node, all I have to do is apply Kcl equations at these 2 particular nodes. So let me call this node voltages as Vx and Vy. And later on, you can see that my Vy is the voltage at this point, which is also point A, because there is nothing connected between point A and this node Vy. So voltage Vy is the voltage at this node with respect to ground. In other words, it's a voltage between point A and ground is also point B. So Vy becomes voltage between point A and B, and hence it is nothing but equal to VTH also, because VTH is also the voltage between the 2 points A and B. So in simple words, all I have to do is find Vx, Vy, and later on we will simply call Vy nothing but VTH. So this is going to be a simple analysis. So let's start with first step, in which we will apply KCL at node X. Now, if you observe carefully, so I'm saying at node X. If you observe carefully, I cannot apply KCL at this particular node because there is a voltage source between the node and the ground, which is the reference point. And hence, I cannot define the current through this particular branch. In fact, if you remember one of the rules that we have used before also, whenever there is a voltage source between a node and the ground point, the reference point, there is no need to apply Kcl equation, because we directly get the value of the node voltage. Vx in this case will be simply equal to 10 volts. So you can see there is no need to find Vx with the help of equations. We get the value of Vx directly. This is not the case with Vy, because you can see there is a voltage source but along with a resistance, so that rule doesn't apply. So when it comes to writing KCL equation at Vy, we will have to consider the currents in all the branches and write down an equation. So let me assume the current directions now. I am taking outgoing currents in these 2 branches, and this branch already has a current source. So let me keep the direction of the current, which is incoming current, to this particular node Y. So let's do it now. I am saying at node Y applying KCL. So outgoing currents equal to incoming currents. The outgoing currents are this outgoing current through 1 ohm resistance is going to be Vy minus Vx divided by 1 plus this vertically down flowing current is going to be equal to Vy minus 5, because we go from positive to negative polarity divided by 2, and this will be equal to the incoming current, that is of 5 amperes. This is equal to 5. Now let us put the value of Vx, which is 10. So Vy plus Vy by 2, I just combine them together. Minus Vx will become minus 10 because Vx is equal to 10 volts, and we get minus 5 by 2 equal to 5. So I can simply solve this equation and get the value of Vy. So that will be Vy into 1 plus half, and this minus 10 goes here, becomes plus 10, plus 5 is 15, this is 2.5, so that's total 17.5, and therefore Vy is equal to, so this will be 3 by 2, which is 1.5, so 17.5 upon 1.5 will give me the value of Vy. Vy becomes 11.667 volts. And as we have already discussed, Vy is nothing but equal to Vth.